My name is François Schmidt. My roll number is 230350100523. I'm a third year student in BSc Honors in Data Science and Artificial Intelligence at IIT Guwahati. This is my trimester 9 project. That's a term project that works on the forecasting of daily equity volatility. The question we're trying to answer is, can machine learning beat classical models? Student ID, put it on the side. So unlike 48, this time I'm just filming directly from Canva. 48, I tried to show the code, and that wasn't doable in Canva. So this I'm just doing Canva because there's not so much to show in terms of data, for example. It's just one-time series about volatility. So let's go. So what's the volatility? The volatility is the size of an asset's daily price swings, basically by how much it moves. That's something that's very important in finance. It drives option pricing, gives an idea about how the risk is, risk appetite to the market participant, whether it's an active market, a slow market, lots of things. It has an immediate impact on the calculation of value at risk, because when you run your time series or when you do your Monte Carlo approximations or your bar models, well, you have volatility somewhere. It's also important for margining, P&L, and risk taking. So there's a key asymmetry there. So the direction of tomorrow's return is basically unpredictable. But what we can see is that days of large volatility are followed by days of large volatility, generally speaking, and same for low volatility. So we can't really say that if the market is going up today, it may go up or down tomorrow, and by how much. But what we know is that if there is a large move today, most likely tomorrow there is a large move up and down. So one of the classical models that we are studying and using in the industry is the gauge model, and it's been around for 4 decades. Now we have machine learning, namely XGBoost, for example, some tree ensemble, and deep learning. So here we have a long, short-term memory neural network that enables to do some form of forecasting. So actually, the idea of using an LSTM was suggested by the person who asked me question during the Viva for T7, and I thought, let's do something on that. It was also about finance and risk, and I thought I would do something similar this time. So we have obviously one harness no look ahead bias, so we don't want to use the volatility in the future to forecast obviously the existing volatility. And here we go. So as I was saying, if we look at the returns, they show no autocorrelation. You can see here, goes up and down. However, if you look at the absolute returns, that the other autocorrelogram on the right here, it shows that there is actually some important correlation, and we call that volatility clustering. So high periods tend to be followed by high period of volatility. So the objective is to compare the basic model, naive model, today's volatility or tomorrow's volatility equals today's volatility. That's very naive assessment. With the gauge, and then with two machine learning methodologies, so XGBoost and LSTM. And what we do is that we look at the usual indicators to see how well the model performs, like RMSE, MAE, and here we introduce a Q-like, as well as the Diebold-Mariano test. So we compare all models. We've got a very clean pipeline. It runs in about a minute over the data period 2008 to 2020, that is used for calibration, and 2026 would be used for testing. And that's also obviously shared by every model. So we have a typical 70-30 split. The data comes from Yahoo Finance. So it's good that we have this data, and that's for the S&P 500 and the daily returns. So the stress window contains the bear market of 2022 and the tariff shock of 2025. The 2008 2020 has the great financial crisis. It's got COVID. So we have vol in the model setting window and crisis in the testing window, which is nice. So tools and technology, the usual, that's written in Python 3.13. We use Panda, NumPy, Y-Finance for the data. We have a PyTorch for the LSTM, the Arch, which is preprocessed for the Garch model, XGBoost, and stats models. The workflow is your typical Jupyter using in VS Code. It's been posted on my GitHub. We have a LaTeX report as required. So the models, first we remind the naive, which is tomorrow's volatility is yesterday's volatility. So usually we actually assess the square return. It's just that in math, very often squares behave in a nice way. You can do derivatives and so on. Not that it matters that much here, but they're nice. Let's put it that way. And also they cleanse the sign of the change, just like apps, but squares are better behaved. Then we have a rolling window of 21 days. We look at the variance over the past 21 days. We have this risk matrix decay for the WMA model, it's 0.94. We have our Garch that's set up as omega plus alpha r square plus beta sigma square, so kind of noise on top of the existing ball. And the E-Garch as well as the GJR Garch model have the leverage effect. So what do we learn? We have the XGBoost with a monthly refit. We have LSTM that is fed with 20 days of features. The share features are the recent return, the realized variance. The share target is what we try to replicate. Log smooth forward variance, and we have the scaling that's only on the trend only scaling, and early stopping for the machine learning models so that we don't overfit. So here I put a lot of snapshots of Garch code, the machine learning code over the two slides here, and the pipeline. So it's just difficult to jump from Canvas to outside Canvas to run, and I wasn't very happy with my previous presentation that way, so I thought I would drop it this time. So next slide, we have a leak-free walk forward. So leak-free is similar to what I was explaining in the trimester 8 presentation. Mean that we don't use the results to forecast. That's what we call a leak, So we make sure that we are really using just past returns and so on. For the periodic graphic, and using the past is this no look ahead thing. The Q-like enables us to check the quality of the numbers along R, MSE, and MAE. And then we have the Diebold-Marino test that shows the gap between two models, if it's statistically real or just a matter of luck. So on to the results, and that's where, again, for the data, there was not much to show in terms of features, as it could have been the case for these previous pressures on loans, for example. But here we have basically the time series, and it's a bit small here, but um, this is overlaid with the simulations from various models. So these are just time series, basically. So we have the evaluation of the different models. So the eGarch 1.1 with a Q-like of 1.5042, the GJR Garch that is a little bit greater, the LSTM that is sensibly greater, and then Garch 1.1, and so on, and XGBoost rolling, and we have our baseline, the naive, that's basically getting a very large number for Q-like, which is just a working model. So that means that our eGarch 1.1 is a better model. We have a quite long sample, so this P that is small is actually meaningful. The LSTM is not working so well, where we have this 0.19. So that gives us more comfort about the eGarch, really. If we move on to the next slide. So when we talk about leverage effect, we have the fact the test window is inclusive of two sharp crashes, 22, 2025. So these are the tariff and some COVID. The Garch family is fit by the maximum likelihood and variance. The learned models train on smoother substitute target. And in terms of data, I think we have roughly 3,250 noisy training days, which favors simple recursions over the neural network. So that's why the neural network is not performing so well. So for the Q-like asymmetry, we have fast reaction to spikes, and the Gauss recursion reacts to very next day. Again, there are some limitations, like in any model, which is a single asset and window, noisy proxy, and modest hyperparameter tuning. Now, if we look at the conclusion and takeaway, we would retain the eGarch 1.1 because it's got the best Q-like, which is the smallest. The learned models are not performing as well. LSTM also attractive because, if we try to do AI, obviously we'd be tempted to be happy if the LSTM performs well, but unfortunately that's not really the case. And what we see that sometimes what's apparently an old model is still working well and still worth considering. So there's a GitHub, the report is in LaTeX, the notebook runs end-to-end, and I can show that during the Viva. Thank you for watching. Goodbye.